When you flip a switch and light spills into a room, it is easy to overlook the invisible force that powers modern life. Yet, the story of electricity and the vast networks we call electrical grids is one of curiosity, rivalry, and relentless invention. To follow this story, we must journey back centuries before glowing bulbs to a time when electricity was more a curiosity than a cornerstone of civilization. Long before wires stretched across landscapes, ancient thinkers observed strange phenomena. The ancient Greeks noticed that when amber was rubbed with fur, it could attract light objects, an early glimpse of what we now know as static electricity. This simple experiment, recorded around 600 before the Common Era by Thales of Miletus, hinted at mysterious forces hidden within everyday materials. For centuries, such observations remained little more than natural oddities, intriguing but not understood. It was not until the 17th century that electricity began to be studied seriously. William Gilbert, an English physician, coined the term electricus to describe the effect produced by rubbing amber. In the 1600s, Otto von Guericke built a machine to generate static electricity, and by the early 18th century, Stephen Gray discovered that electricity could travel through some substances but not others, an early recognition of electrical conduction. These scattered experiments, though primitive, laid the groundwork for a new science. Benjamin Franklin's legendary kite experiment in 1752, though often dramatized in popular imagination, demonstrated that lightning was a form of electricity. Franklin's insight bridged the gap between the natural world's spectacular displays and the subtle charges scientists observed in the laboratory. His work, along with that of his contemporaries, began to reveal that electricity was not just a curiosity, but a force that could be harnessed and understood. The next great leap came with Alessandro Volta's invention of the electric battery in 1800. Volta created a device capable of producing a steady flow of electric current, a fundamental breakthrough. For the first time, electricity could be generated on demand rather than captured fleetingly from static charges or lightning. Volta's battery, or voltaic pile, sparked a new era of experimentation and discovery. Michael Faraday's work in the early 19th century advanced the science of electricity even further. Faraday demonstrated the close relationship between electricity and magnetism, showing that moving a magnet through a coil of wire could generate electric current, a process now known as electromagnetic induction. This principle is at the heart of modern electricity generation, from the smallest dynamo to the largest power plant. By the late 1800s, inventors and entrepreneurs were racing to turn these discoveries into practical technologies. Thomas Edison, with his relentless focus on commercialization, developed the incandescent light bulb and built the first commercial power plant in the United States. In 1882, his Pearl Street station in New York began supplying electricity to a handful of local customers, marking a pivotal moment in history. For the first time, electricity flowed not as a novelty or isolated experiment, but as a service delivered to homes and businesses. Edison's early system relied on direct current, which had significant limitations. Power could not be transmitted efficiently over long distances, so generators needed to be located near the point of use. As cities grew and demand for electricity surged, these constraints became increasingly problematic. At almost the same time, a different vision of electrical power was emerging. Nikola Tesla, a brilliant inventor and engineer, championed alternating current, which could be transmitted over much greater distances. The key to alternating current success was the transformer, a device that could step voltage up for transmission and then back down for safe use. The invention of the transformer marked a turning point. With alternating current, electricity could be generated in one place and set miles away, making it possible to build large, centralized power plants and connect communities in a network, a grid. The battle between Edison's direct current system and Tesla's alternating current approach became known as the War of the Currents. It was a chaotic and highly publicized rivalry, with both sides making dramatic claims about the safety and effectiveness of their technologies. Ultimately, alternating current prevailed, largely because of its superior ability to transmit power efficiently over long distances. As the 19th century drew to a close, the world's first electric grids began to take shape. In London, Sir Coots Lindsey and the London Electricity Supply Corporation grappled with the daunting technical and economic challenges of delivering power to a growing, electrified city. Across the Atlantic, Edison's Pearl Street station served as the model for early American grids, even as the system's limitations spurred rapid innovation and experimentation. The development of grids was often fragmented and fiercely competitive, with multiple companies laying cables, sometimes right on top of one another, creating a tangled web of wires and rivalries. Hydroelectric power soon emerged as an important energy source, especially in areas with abundant water resources. The use of water to generate electricity allowed for larger power plants, feeding more homes and industries. Cities began to glow with electric lights, and factories hummed with new machines. The pace of electrification was astonishing, especially in urban centers. The promise of cheap, reliable power was transforming daily life, shrinking the darkness of night and fueling the engines of commerce. Yet, the transition to widespread electrification was far from smooth. Early systems were often isolated, serving only a small cluster of customers. Over time, these point-to-point networks began to link together, forming the first true electrical grids. The concept of a grid, a network of interconnected power sources and customers, offered tremendous advantages. It allowed for greater reliability, as failures in one part of the system could be compensated for by power from another. It also enabled the rise of vertically integrated companies, which controlled generation, transmission, and distribution, bringing economies of scale and stability to the supply of electricity. The birth of the grid was not a single moment, but a process of relentless adaptation and innovation. From the first flicker of static in ancient Greece to the hum of dynamos in Victorian cities, the story of electrical grids is a testament to human ingenuity. Each breakthrough built upon the last: Thales' musings on amber, Franklin's stormy experiments, Volta's battery, Faraday's induction, Edison's power plants, Tesla's alternating current, and the engineers who wove these discoveries into the fabric of civilization. Today's electrical grids are the descendants of these early efforts, still evolving and adapting as new challenges and technologies arise. The world's cities, industries, and homes are bound together by a vast, invisible web of wires and currents, a legacy of curiosity, competition, and collaboration that continues to shape the course of civilization. The journey from sparks and static to the birth of the grid is not just a tale of technology, but a story about how people, driven by wonder and necessity, learned to harness the forces of nature and illuminate the modern world. Imagine for a moment standing on a hill at twilight, gazing out over a city as it flickers to life. One by one, streetlights blink on, homes glow warmly, and entire neighborhoods hum with invisible energy. Behind this everyday miracle lies one of humanity's grandest engineering achievements, the electrical grid. This sprawling, intricate network quietly knits together power plants, transmission towers, substations, and countless wires, carrying electricity across vast distances into the hands of individuals, families, and industries. To understand how civilization stays lit, powered, and connected, we must unravel the science and engineering behind the wires that stretch across the world. At its core, the electrical grid is simple in concept but staggering in execution. The journey of electricity begins at the site of generation. Here, energy is coaxed from fuel sources, spinning turbines in wind farms, churning water in hydroelectric dams, whirring gas turbines, or the steady pulse of nuclear reactors. Each type of power plant harnesses a physical process to spin a generator, transforming mechanical energy into electrical energy. While the details of each plant's operation can differ dramatically, their output is essentially the same: electricity ready to embark on its long journey toward consumers. But the electricity produced inside a power plant cannot simply be piped directly to your home. First, it must enter the transmission system, a vast superhighway designed to move enormous quantities of electricity over long distances. Transmission lines are the giants of the grid, strung across the landscape atop steel towers, sometimes stretching hundreds of miles, their cables humming with energy at voltages that can exceed several 100,000 volts. The reason for such high voltage is rooted in physics. As electricity travels, some energy is lost as heat. By increasing the voltage, the current can be reduced for a given power level, which helps minimize those losses and allows electricity to travel farther with greater efficiency. To achieve these high voltages, engineers rely on transformers. Those boxy, often humming pieces of equipment that step the voltage up before electricity leaves the generating station. Once in the transmission system, electricity may pass through a series of substations, each serving as a relay point, sometimes shifting the voltage or routing power in new directions. Transmission infrastructure is robust by design. Steel structures, high-voltage cables, insulators, circuit breakers, and specialized switches all work together to ensure the safe, reliable passage of electricity over great distances. Transmission, however, is only half the journey. As electricity approaches the places people live and work, it must be prepared for everyday use. This brings us to the distribution system, the web of smaller wires and poles that fan out across cities and towns. At the edge of the transmission network, substations use transformers to step down the voltage, making it safe for local distribution. From there, electricity travels along lower voltage lines, weaving through neighborhoods, snaking underground or overhead until it finally arrives at its destination. This distinction between transmission and distribution is crucial. The former covers long distances at high voltages, while the latter manages the final, local delivery at voltages suitable for homes and businesses. The structure of the grid itself is immense. In North America, for example, the system is divided into three major interconnections: Eastern, Western, and the Electric Reliability Council of Texas, each operating largely independently but with some ability to share power at their borders. These interconnections are not only feats of engineering but also of coordination, as each region must constantly balance its own supply and demand, sometimes exchanging electricity with neighbors when needed. Behind the scenes, a hidden choreography unfolds every second of every day. Electricity cannot be easily stored at scale in the traditional grid, so the amount generated must always match the amount consumed, almost perfectly, in real time. This continuous balancing act falls to specialized organizations known as balancing authorities. These entities monitor the grid, forecast demand, and instruct power plants to ramp up or down, ensuring that supply and demand remain in harmony. If too much electricity flows into the grid, frequency rises above the standard, usually 60 Hz in North America. If supply falls short, frequency drops. Even small deviations can cascade into instability, risking outages or equipment damage. To help maintain this delicate balance, grid operators use an array of strategies. They keep reserve margins, a buffer of extra capacity that can be called upon quickly if demand spikes or a power plant goes offline. They also coordinate with neighboring grids, exchanging electricity across interconnections when needed. Storage technologies such as batteries are increasingly being deployed as grid shock absorbers, able to take in energy during periods of surplus and release it when demand surges. Yet, even with these tools, the work is never simple. The grid must respond not just to predictable rhythms like the morning wake-up call or the evening electricity rush hour as people return home, but also to sudden changes in weather, equipment failures, or unexpected shifts in consumption. The grid's inner workings rely on a host of technical measures. Inertia, provided by the spinning masses of traditional generators, helps stabilize frequency in the face of sudden disturbances. Voltage must be carefully managed to ensure the safe and efficient operation of equipment. Ancillary services, specialized controls, and support functions help keep the grid stable, managing everything from frequency regulation to voltage support. Protective devices such as circuit breakers and relays stand ready to isolate faults, preventing small problems from ballooning into widespread outages. Modern grids are also evolving. While most electricity is still moved using alternating current, which allows voltages to be easily transformed up and down, direct current lines are sometimes used for particularly long distances or to connect separate grid regions. New smart grid technologies are being introduced, embedding sensors, automated controls, and digital communication into the network. These advances promise greater flexibility, efficiency, and resilience, especially as more renewable energy sources like solar and wind are connected to the grid. Integrating these variable sources presents new challenges, requiring more agile management and sometimes significant investment to ensure the grid remains reliable. Regulation and oversight are fundamental to grid operation. In the United States, federal agencies such as the Federal Energy Regulatory Commission and the North American Electric Reliability Corporation set rules and standards for how the grid is built, maintained, and operated. Regional organizations, including independent system operators and regional transmission organizations, oversee the day-to-day operation of specific portions of the grid, coordinating the flow of electricity and ensuring compliance with reliability standards. All of this complexity serves a simple, vital purpose: to keep the lights on everywhere from bustling cities to the most remote rural outposts. The grid's wires, transformers, and control centers form the backbone of modern civilization, enabling everything from the hum of industry to the quiet comfort of a lamp glowing in the night. Yet, this system is not static. It must continually adapt as technology advances, as patterns of use evolve, and as societies push toward new energy frontiers. So, the next time you flip a switch and light spills into a room, remember the journey that electricity has taken. From the thrum of turbines in distant power plants, through the silent march of high-voltage lines, across substations and into the capillaries of local distribution, the grid stands as a testament to human ingenuity and the ceaseless drive to connect, create, and illuminate. The story of civilization's growth is, in no small part, the story of wires stretched across the world carrying not just power, but possibility. Imagine a world at dusk, the sky darkening over both city and countryside. With a simple flick of a switch, living rooms, factories, and bustling streets are illuminated, an act so routine that its significance often goes unnoticed. Yet behind that ordinary gesture lies one of the great engines of progress, the electrical grid, quietly transforming daily life, reshaping economies, and expanding the boundaries of what is possible. In the early days of electrification, the glow of an electric bulb was a marvel reserved for the privileged few. But as the grid rapidly expanded, electricity shifted from a luxury to a necessity, woven into the very fabric of modern life. By the middle of the 20th century, electrification rates in many developed countries soared, bringing light, warmth, and power to millions. This transformation was profound. Homes could be kept bright and safe after sunset. Domestic chores, once laborious, became easier and faster. The steady hum of refrigerators preserved food, electric stoves simplified cooking, and radios and televisions opened new windows to the world. The grid did not merely power devices, it powered aspirations, opportunities, and connections that shaped the rhythms of everyday life. Industry was forever changed as well. Electrification became a catalyst for industrial development on a scale previously unimaginable. Factories, once limited by steam and water power, could now operate more flexibly and efficiently. Research shows that as electricity became widely available, the number of firms and workers in manufacturing increased and industrial output surged. Productivity gains arrived swiftly and proved durable, especially in regions near abundant hydroelectric resources. Electricity enabled new technologies, assembly lines, electric motors, precision tools that fueled waves of innovation and made mass production possible. This surge in economic growth was accompanied by a cultural shift. Electrified industry inspired awe and optimism, symbolizing a future shaped by human ingenuity. The societal impact of the grid reached far beyond city limits. In the United States, the Rural Electrification Act marked a turning point, bringing power to millions of rural families who had been left in the dark, both literally and figuratively. Before widespread rural electrification, life outside urban centers was defined by hard manual labor and limited access to education, healthcare, and information. The arrival of electricity transformed rural America, mechanizing agriculture, making homes more comfortable, and connecting isolated communities to the broader world. Yet this transformation was not without challenges. Rural areas often relied on aging distribution systems, and the vast distances between farms and small towns made infrastructure investments costly and technically demanding. Rural electric cooperatives rose to meet these challenges, owned and governed by the very communities they served. Still, these cooperatives continue to grapple with the legacy of old infrastructure and the economic pressures of modernization. The need for resilience in the face of storms, wildfires, and shifting demand remains a constant concern. The story of electrification is also a story of inequality, of who benefits, who is left behind, and what it means to be denied reliable, affordable power. Despite remarkable progress, the world remains sharply divided. According to recent estimates, 730 million people still live without access to electricity. For many more, approximately 1.18 billion, energy poverty is a daily reality. They may have a connection to the grid, but it is unreliable, expensive, or insufficient for meaningful use. The consequences ripple through every aspect of life. Inadequate energy access limits educational opportunities as children struggle to study by dim candlelight. It constrains healthcare, with clinics unable to refrigerate vaccines or power essential equipment. Economic advancement stalls when businesses cannot rely on steady power to run machinery or computers. The divide is especially stark between urban and rural areas, where the cost of extending service and maintaining infrastructure can be prohibitive. These inequities are more than technical or economic. They are deeply social, affecting health, gender equality, and the chance to escape poverty. Where energy poverty persists, so too do preventable illnesses, environmental hazards from burning wood or charcoal, and the burden often borne by women and children of gathering fuel. Access to reliable electricity is now recognized as a foundation for achieving broader development goals, from reducing poverty to improving education and health outcomes. The United Nations has made universal access to energy a central pillar of its sustainable development goals, yet progress remains uneven and fragile. Investment and innovation are urgently needed to close these gaps and ensure that the benefits of electrification reach everyone, everywhere. Even as the grid has delivered extraordinary social and economic gains, it has also brought new environmental and health challenges. The majority of the world's electricity is still generated by burning fossil fuels, coal, oil, and natural gas. These power plants emit greenhouse gases that drive climate change, as well as pollutants like mercury and particulates that harm air quality and public health. The impact is not abstract. Communities near coal-fired plants experience higher rates of respiratory illness, while emissions from ships and port facilities contribute to urban air pollution. The grid's reach, once celebrated as a symbol of progress, now faces scrutiny for its environmental footprint. Yet the grid is also a powerful tool in the pursuit of a cleaner, more sustainable future. Electrification of industry and urban activities offers a path to decarbonization, allowing societies to phase out fossil fuels in favor of cleaner energy sources. As electric motors replace combustion engines in factories and electric vehicles take to the streets, the potential for reducing emissions grows. Studies have shown that electrification can yield immediate and lasting reductions in air pollution and climate impacts, especially when paired with investments in renewable energy. Economic models suggest that these transitions can also deliver tangible benefits, such as a 2% increase in real income, as stronger economic growth accompanies cleaner, more efficient energy use. Grid modernization is central to realizing this promise. Around the world, utilities and governments are investing in smarter infrastructure, aiming to make the grid more reliable, resilient, and responsive to changing needs. Upgrades include advanced sensors, automated controls, and digital communication systems that can detect and respond to outages in real time, integrate renewable energy, and empower consumers to manage their energy use more effectively. Case studies highlight the positive impact of targeted electrification efforts, particularly in low-income communities, where access to electric public transport or affordable heating can reduce pollution and improve quality of life. In rural Indonesia, for example, carefully designed electrification projects have not only expanded access but also spurred productive uses of electricity, powering small businesses, improving agricultural output, and supporting structural change. Yet progress remains uneven, and the challenges are formidable. Many rural electric cooperatives, especially in developing countries, face the dual pressures of modernizing aging infrastructure while keeping service affordable for their members. The complexities of integrating new technologies, the persistent gap between urban and rural service quality, and the need for sustained investment all point to a long journey ahead. The grid, once a marvel of engineering, is now a work in progress, a dynamic system whose evolution will shape the future of society, the environment, and the global economy. As the sun sets and lights flicker on across continents, the story of the grid is still being written. It is a story of ingenuity and ambition, of obstacles overcome and new frontiers yet to be reached. The wires that span fields and cities do more than carry electrons. They carry hope, challenge, and the promise of a more connected and equitable world. The grid's impact on society is both a triumph and a task unfinished, a testament to what can be achieved and a reminder of the work that still lies ahead. Electricity's journey from novelty to necessity has transformed civilization, yet the grid's future promises both turbulence and ingenuity. In the early 21st century, the electrical grid stands at a crossroads. It is a marvel of reliability, but also a patchwork of aging wires, substations, and software now expected to shoulder new burdens. The challenges are formidable, integrating vast amounts of renewable energy, fending off increasingly sophisticated cyber threats, accommodating surges in demand from data centers and electric vehicles, all while maintaining the resilience and affordability society depends on. The grid, once a one-way path from power plant to home, is evolving into a dynamic, many-headed entity, smarter, more connected, yet acutely vulnerable to new risks. Consider the sheer complexity of keeping the lights on. The grid must respond not only to predictable daily surges in demand, but also to the unpredictable whims of weather, shifting consumption patterns, and the ebb and flow of generation from thousands of new wind turbines and solar panels. The inexorable rise of renewables is both a triumph and a technical headache. Solar and wind, for all their environmental promise, are variable by nature. The sun sets, clouds pass, winds calm. On some days, renewables flood the grid with electricity. On others, they vanish when needed most. Integrating these sources requires new tools, smarter forecasting, and nimble management. Without careful planning, a sudden drop in wind or an unexpected cloud bank can leave grid operators scrambling, risking instability or even blackouts. Energy storage is emerging as a vital solution. Batteries, particularly lithium-ion systems, can soak up excess solar power during the day and release it after dusk. Pumped hydro, where water is lifted to a reservoir when energy is plentiful and released to generate electricity when demand peaks, remains a workhorse. Yet even these technologies must be carefully woven into the fabric of the grid. Storage must be distributed strategically close to where renewables are generated and where demand is highest to truly smooth out the bumps. As more communities and businesses install their own solar arrays and batteries, the flow of electricity is no longer strictly top-down but bi-directional, challenging old ways of managing voltage, frequency, and reliability. The pressure on the grid is mounting not only from renewables but also from surging demand in unexpected sectors. Data centers, the humming, air-conditioned fortresses of the digital age, are voracious consumers of electricity. With artificial intelligence and cloud computing on the rise, these centers are multiplying, often clustering near major cities and transmission corridors. Experts warn that if reliable generating capacity is retired too quickly, outpaced by the growth of these power-intensive facilities, grids could face mounting risks of supply shortfalls, especially during extreme weather or unexpected surges in consumption. Climate change, too, is reshaping the grid's risk landscape. More frequent and intense storms, wildfires, and heat waves strain infrastructure and can trigger cascading outages. Transmission lines that once seemed robust are now threatened by drought-driven wildfires or ice-laden winter storms. Utilities and regulators are grappling with how to harden these networks, debating investments in undergrounding lines, expanding weatherization, and building new redundancy into transmission corridors. At the same time, expanding and modernizing the grid to accommodate renewable power often means constructing new high-voltage lines across contentious landscapes, pitting clean energy goals against local opposition and regulatory bottlenecks. Layered atop these physical threats is an invisible, rapidly growing menace: cyber attack. As the grid becomes smarter, filled with sensors, digital meters, and automated controls, it also opens new doors to attackers. Cybersecurity analysts report a doubling of attacks on the power sector in recent years, with hackers probing for weaknesses that could let them disrupt operations or even destabilize entire regions. Smart inverters, essential for integrating solar and wind plants, have themselves become potential targets. If compromised, they could be manipulated to destabilize the grid in orchestrated attacks, potentially blacking out thousands or even millions of customers. The grid's digital transformation, while necessary for efficiency and flexibility, requires a parallel investment in cyber-physical protection. Artificial intelligence is now being pressed into service, not just to forecast demand or optimize renewable integration, but to detect and neutralize both physical and cyber threats in real time. Artificial intelligence-powered monitoring platforms can spot anomalies in the torrent of data streaming from substations and sensors, flagging unusual patterns that might indicate an attack or equipment failure. Yet even the most advanced tools cannot guarantee perfect security. The challenge is to build a system resilient enough to withstand and recover from inevitable breaches. Regulators and policymakers are responding with new rules and programs. Federal initiatives aim to strengthen both physical and cyber defenses, requiring utilities to develop recovery plans and invest in more robust systems. There is growing recognition that, in an era of interconnected threats, resilience is as critical as reliability. The grid must not only deliver power without interruption, but also bounce back swiftly from disasters, whether natural or man-made. Out of these challenges, a wave of innovation is cresting. The concept of the smart grid has moved from buzzword to blueprint. Smart grids embed advanced sensors, digital meters, and automated controls throughout the network. They can detect outages almost instantly, reroute power around damaged lines, and even allow consumers to adjust their usage in response to real-time price signals or grid needs. In some regions, utilities are deploying advanced distribution management systems that forecast demand down to the individual meter, optimizing the dispatch of not just power plants but fleets of batteries and electric vehicles. One of the most intriguing trends is the rise of decentralized energy. Where once electricity flowed from a handful of massive plants, today it increasingly comes from thousands of smaller sources: rooftop solar panels, community wind farms, home batteries, and even electric cars capable of feeding power back into the grid. This decentralization brings resilience. A network built on many small nodes is less vulnerable to single points of failure, be they storms, cyber attacks, or equipment faults. It also empowers communities and individuals, allowing neighborhoods or businesses to keep the lights on independently during broader outages, or to trade electricity locally, creating new markets and opportunities. Decentralized systems are also being explored as a hedge against climate volatility and cyber threats. By reducing dependence on long, exposed transmission lines and central control systems, these grids within the grid can act as shock absorbers, keeping critical services running when the main system falters. Some analysts highlight the environmental, social, and governance value of this approach, as decentralized energy can foster local investment, cut emissions, and enhance energy equity. Virtual power plants, Networks of distributed resources controlled by sophisticated software are already being deployed. These platforms aggregate the output from hundreds or thousands of small-scale batteries, solar arrays, and flexible loads, dispatching them as a coordinated unit to support the grid. During periods of peak demand or grid stress, they can inject power, reduce consumption, or shift usage to times of surplus, smoothing the overall system and reducing reliance on fossil fuel backup. Looking ahead, further digitalization seems inevitable. Sensors and software will increasingly orchestrate the dance between generation and demand, integrating electric vehicle charging, managing bottlenecks, and balancing the system in real time. The Internet of Things, artificial intelligence, and high-speed communications will become as essential to the grid as copper wire and steel towers once were. But with this intelligence comes new complexity and the imperative to manage risk at every level, from local substations to national control centers. Civilization's relationship with electricity, then, is poised for another profound shift. Where the grid was once an invisible utility, always assumed but rarely noticed, it is now becoming a living system, responsive, adaptive, and deeply entwined with the fabric of society. The stakes are high. The reliability of everything from hospitals to data centers, the security of critical infrastructure, the pace of decarbonization, and the resilience of entire communities all depend on how well the grid evolves. The challenges are daunting, but the innovations underway, smart grids, decentralized energy, advanced storage, and cyber-physical defenses, offer a glimpse of a future where the flow of electrons is not just a technical feat, but a reflection of collective ingenuity and shared destiny.